And here comes the stress tensor as an example. The stress tensor is a classical example of the use of tensors in physics. It has to do with the stress on a material object. The stress can be applied to a surface either in the perpendicular direction, these are the red arrows, or in the parallel direction to the surface, these are the purple arrows. Now, in the case of the perpendicular direction, the stress leads to compression or expansion. You have this stress that is perpendicular to the surface, so it's compressing it. And here, it's pointing on the opposite direction, so it's expanding it. This perpendicular stress is a pressure. Now, in the parallel direction, the surface is transported, distorting the shape in the direction of the applied stress. This parallel stress is what we call shear. So there you go. The stress can be decomposed into the perpendicular stress, which is a pressure, and a parallel stress, which is the shear. Let's now attempt to mathematize this stress. The stress has units of force per unit area. So it seems clear thus that the stress, let's call it sigma, times the area should equal a force. That means that in magnitude, we're not caring about the direction yet. In magnitude, you can write that the magnitude of the force is proportional to the magnitude of the stress and the magnitude of the area. That is, the stress area product should be associated with the applied forces that are producing the stress. Now we know that the force is a vector, and we also know the area can be represented as a vector by associating it with a direction. You can define the differential area dA, that is a vector with magnitude equal to the size of the area and direction that is normal to the area element. So in this equation here, dF equal to sigma times dA, stress sigma can be either a scalar, a vector, or something else. Now, if sigma was a scalar, if the stress was a scalar, then that means that the force would always be in the same direction of the normal to the area. And while this would be okay to describe the pressure, this cannot describe the shear. It does not account for the parallel stress.